Having studied equation of continuity, let us look at Bernoulli's equation. Bernoulli's equation is for a steady flow of fluid. So, this was written down by Daniel Bernoulli. So, this is and from 1708 1700 to 1782. So, he wrote down Bernoulli's equation which is simply a statement of conservation of energy. Let us see how we can derive this equation or the equation that he has written down, what applications do they have with physical systems, or how it is of help in measuring the flow of a fluid. And as I said, that this is for a steady or a streamline flow, steady or a streamline flow of a liquid, of an incompressible liquid. So, in order to derive Bernoulli's equation, let us take this picture. So, this is the fluid flow through a pipe. So, there is an upstream flow. Call this region as, so I am considering an elemental fluid in this region and also considering an elemental fluid in this region. Let us call this as region 1 and call this as region 2. This is at a height h2, this is at a height h1, let us write h1 here, and the pressure that is recorded here is say P1. It is recorded by a pressure gauge. I am not drawing the pressure gauge, but the pressure is P1, which is determined by a pressure gauge. The pressure is P2 here, and so it is moving upstream. So, the velocity flow is in this direction here and it is in this direction here, which are respectively V2 in region 2 and V1 in region 1. And we also have the areas of cross sections are different, and let the area of cross section be A2 here and the area of cross section be A1 here. So, this is the situation. So, this is only element, the fluid is drawn here, which is flowing through a pipe. Pipe is not of importance to us. We are only considered, we are considering the mass. So, this fluid has mass m. And this fluid is flowing upstream. The heights from some where the height equal to 0, some reference line, the heights are h2 and h1 and the velocities are shown there. So, now this fluid is of course under gravity. So, the energy is constant and the total energy, so E is given by the kinetic energy of the fluid plus the potential energy. So, this total energy is conserved, and so this is equal to half m v square plus m g h where V is the velocity at any arbitrary point along the flow, and h is the height, corresponding height measured from this reference level. So the energy difference between the region 1 and region 2, so energy difference between region 1, I will just in short write it as R1 and R2, that is region 2, is E1 minus E2. This is equal to half m V1 square plus mg H1 minus half m V2 square plus mg H2. So, this is the energy difference between the two regions, region 2 here and region 1 here. So, they are given by E1 minus E2 and these are the kinetic energy and the potential energy at region 1, kinetic energy and potential energy of the liquid or the fluid in region 2. Now, this energy difference should be doing some work, and we can calculate that work by it should be spent in doing some work rather. So, this energy should be spent in doing some work, and by the work energy theorem, this work done that we just talked about is equal to E1 minus E2, which is equal to half m V1 square plus mg H1 minus half m V2 square plus mg H2. Now, we can also find the expression for this W, an alternate expression for W, which is the work done in moving the fluid from a point to the neighboring point. For that, let us take a small element of fluid, very small, it is only overemphasized. This has an area of cross section A and the length to be L, right. So, I am only taking a small elemental fluid which has say area delta A and the length of this to be L. So, this much of fluid that I am considering, and now there is some pressure here in this end, let us call that pressure as P. Now, there is a bigger pressure at the bottom point, let us call that as P plus delta P. So, this is the pressure here and this P is the pressure here. So, we can erase some of these things here, and we will have a pressure at, let us call this point as O and this point as O prime. So, pressure at O is equal to P plus delta P, and pressure at O prime equal to P. Okay. So, now the force that is acting in the upward direction at the point O is equal to, so force at O equal to P plus delta P into let us just call it as A instead of delta A. So, we know that the cross section, the area of cross section here in this small portion, which is assumed to be constant, even though the whole liquid flow, the filament does not have a constant cross section, but since we have taken this area to be small enough, or rather this region to be small enough, we can take that to be constant, and let us call that as some A. So, this is the force acting and the direction is upward as it is shown here. So, this is the direction of force at O, sorry. And there is also a force that is acting here, which let us call that as F O prime. So, force at O prime it's equal to P A. So, the work done, or rather the difference in force, so difference in force between O and O prime, O and O prime, or you can call it as O prime and O, it is equal to P plus delta P A minus P A, which is equal to a delta P A. Now, this force will be spent in doing the work that we have mentioned here, and for this force to push this liquid column, we would just need the force, so the work done is W is equal to this delta P into A into L. This is the distance in moving the liquid film go from here to here, and this will be that, which is equal to delta P and V, where V is the volume of this small portion that is drawn here. So, this has a volume V, and so the work done will be delta P into V. So, now we will have to equate the work done that is written here on the right hand side to the work done that is there. You might wonder that this V is not, so this will be an elemental work. So, that is delta P into V. Now, in order to transport the liquid film from region 2 to region 1, we will have to sum over all these elemental work done, and that will simply be equal to, so the entire work done will be P2 minus P1 into V, where P2, so we are talking about the work done to take the liquid or the transport the liquid from region 2 to region 1, where the pressure difference is equal to P2 and P1. P2 is at a larger pressure because the liquid is flowing upstream. So, P2 minus P1 multiplied by V should be equal to my E1 minus E2, which is equal to half m V1 square plus mg H1 minus half m V2 square plus mg H2. We can divide this entire equation by V, so that my m over V becomes rho, which is the density of the liquid that is flowing through the pipe here, and then we can simply write as P1 plus half rho V1 square plus rho g H1 equal to P2 plus half rho V2 square plus r rho g H2, and this is known as Bernoulli's equation. So, in a generic sense we can write that, so this is called as a pressure head, this is called as a kinetic head, this is called as a potential head. So, we can write that in a streamline flow, the pressure plus half rho V square plus rho g H will remain constant at all points throughout the flow of the fluid. So, this is written down by Bernoulli somewhere in the 18th century between 1700 to 1782, and this has a lot of applications. So, let us see one application to begin with, and that application is called as Venturi meter. I will tell you what it is. So, we study the application of Bernoulli's equation, and this is applied to a device called as Venturi meter. And what does Venturi meter do? Venturi meter measures the speed of the flow of a certain liquid through a pipe. So, let us just write that. So, a Venturi meter is a device which measures the speed of a fluid within a pipe. So, there is a pipe here. Let us draw the pipe, and let us just say that this has the area of cross section, is a uniform pipe, the area of cross section of the pipe being A2, the velocity of water through this is V2, and suppose that is known, V2 is known, that is you have connected it to a water supply, and you know that what is the speed of water that is entering through this area of cross section and would leave eventually through the other end, and say we know V2. Now, we need to know the what we can do is that, so Venturi meter is a device which is like this. It's not drawn exactly to scale, but what I meant to do is that this is my A2 this is my A2, same as the cross section of this initial pipe, and I have put a constriction here, and this is the region which is called as Venturi meter. So, this is A2 as well, and this has an area of cross section which is A1, and I want to find the speed or the velocity of the fluid through this constriction, and this part of the device is known as. So, I introduce a Venturi meter inside the pipe. So, this is introduced inside the pipe, and we need to know the flow of the liquid through this constricted part. So, let us call this, so this is A1 and this is V1, and again this is V2. Now, it is clear that we can measure pressure at this place by introducing a pressure gauge. Okay. So, this will measure pressure here, and this will also say measure the pressure here by introducing another pressure gauge. So, this measures the pressure P2 and this measures the pressure P1. Now, because of equation of continuity, we know the equation of continuity says that the flux or the area of cross section into the velocity of the fluid is constant for an incompressible fluid. So, A into V is constant, where A is the area of cross section and V is the velocity. So, we have for these 2 points we have A2 V2 equal to A1 V1, since A2 is greater than A1, I have to have V1 to be greater than V2. So, the speed of the fluid as it enters the constriction will be larger than the speed of the fluid at other parts. Now, because of this, the pressure actually falls. The pressure falls here. So, my P1 will be less than P2, and we can apply Bernoulli's theorem and we can write that P1 plus half rho V1 square equal to P2 plus half rho V2 square. Note that we have neglected the potential head here, because we can think that there is no effect of gravity in this case, and say it is resting on a table, and the surface of the table marks the potential energy, where the potential energy is 0. So, we have not written the potential term here, or the potential head, but however, from Bernoulli's equation, the pressure pressure head plus the kinetic head at region 1 should be equal to the pressure and the kinetic head at region 2. And if we have that, then we can simply, if we know V2, as I said at the beginning, if we know V2 and we have measured P1 and P2, so V1 can be determined. So, this is a direct application of Bernoulli's principle. So far we have talked about what happens to a point that lies completely submerged in a liquid. That is, for points which are well within the liquid, we have seen the calculation of pressure and various things that we have talked about, Pascal's law and other things. Now, we want to know that what happens at the surface of the water, and in fact, the surface of the water or a liquid also has very interesting properties. So, what we now want to consider is, let us take a vessel of water, container of water, containing water, and there is this surface, and the surface, the properties of the surface is what we are going to see now, and this comes under the heading as surface tension. So, before we start surface tension, you might have noticed that, let us discuss something which you have seen in real life. Say you have closed the tap, but the tap is, before it stops issuing water completely, the last drop of water which almost hangs on to from the end of the tap assumes a spherical shape. Okay. Also, you might have seen that the dew on the grass, as the winter sets in, the dew on the grass also assumes a spherical shape. So, this tells you that the spherical shape is related to the surface of the liquid. We know that liquid itself does not have a shape, and it takes the shape of the container. So, why are these the last drop hanging on to the water tap and the drop that is the dew that is forms assumes such a spherical shape? More examples. Take a small balloon filled with water. So, a balloon filled with water, and say it is a small balloon, let us not make it too large, or even a needle. Okay. So, these are two examples which you can see that they float on the surface of the water, even though they are more dense than the water itself. So, why does this happen? It happens because of surface tension. Okay. So, it is a property of the surface, and let us see what kind of property it is. Basically, the surface of the water, it behaves like a membrane. You might have seen membranes, say a common thing to see is the top membrane of a tabla, where you play the tabla, that the membrane, or there are membranes that are taught in biology. So, it acts like a membrane which is under tension. So, surface of a liquid acts like a membrane under tension. And this tension that we have just talked about here, this tension acts parallel to the surface, and it acts along any line on the surface as if it is trying to pull open the surface. So, that is the surface tension, that is the definition of surface tension. It acts parallel to the surface, acts along any line which is on the surface, and as if it is trying to pull open the surface, tending to pull open the surface. So, this tension is called as surface tension, and it is defined as the force per unit length, and this has unit as Newton per meter, and this is the definition of surface tension, that it is force divided by force per unit length, and the unit, as you understand, is in Newton per meter. Let us try to understand that why does surface tension arise, or what are the consequences of surface tension. For that, let us consider this U-shaped tube. So, this U-shaped tube has a movable rod, say for example, and this movable rod encloses some liquid. Okay. So, there is a thin film of liquid that is enclosed by this moving rod, and you require some force in order to pull this rod. To pull this movable rod, you need some force. So, it is a U-shaped tube encloses a thin film of fluid by a movable rod. So, as we pull this movable rod, the surface area of this liquid film increases, and let us take a small element of fluid, and this, let us say, a cylindrical element of fluid, and the force acting. So, all these, so there is a surface tension acting on the surface. This is a thin film, it is not a volume fluid that we are considering, it is a thin film, just a surface, and all these, the surface tension is acting at all points parallel to the surface. So, let us take one small column here, and consider this force F acting on this, which increases the surface area, this will increase the length of both these sides of the tube. So, that tells you that the surface tension is S here, S here. So, S is equal to F over 2L, 2L because we have talked about a film which has the two sides of the two dimensional cylinder that we are talking about. So, the surface tension is defined as F over 2L. So, 2L is the increase in length So, this is the surface tension, definition of surface tension, S is equal to F over 2L, and apparatus of this kind actually can be used to determine the surface tension. See, if we know F and of course, we know L by the amount it increases as you pull this, as you apply this force. Suppose F and L both are known, so you can simply get S using this formula. And let us now write down the surface tension due to some common fluids that we come across every day. So, let us just make a table as we have done many times earlier. So, this is we will write down the substance and we will write down the surface tension, which in Newton per, in units of Newton per meter. So, remember surface tension is a function of the temperature. So, you need to mention the temperature at which you are talking about the surface tension. So, this is mercury at 20 degree centigrade, mostly we will talk about 20 degree centigrade, it is equal to 0.44. Then blood, again this is at not at 20 degree centigrade, this is at 37 degree centigrade, which is equal to 0.058. And then ethyl alcohol, again at 20 degree centigrade, is equal to 0.023, and soap at 20 degree centigrade, again it is equal to 0.025. Now, water, let me write it separately here. So, again substance and the surface tension in Newton per meter. So, water at 0 degree centigrade, which is equal to 0.076, water at 20 degree centigrade 0.072, water at boiling point, which is 100 degree centigrade, equal to 0.059. It is interesting to see that which we will not discuss at length, that the surface tension decreases with increase in temperature. So, it goes down from 0.076 at 0 degree centigrade to 0.059 at 100 degree centigrade. So, let us understand this surface tension little better. I just give you one more view of this. Mercury at 20 degree centigrade is 0.44, which is at least something like 1 order of magnitude more than the other substances that we have considered. Blood at 37 degree centigrade is 0.058, ethyl alcohol at 20 degree centigrade is 0.023, and soap at 20 degree centigrade is 0.025, and the water, the values for water are given here. All right. So, let us take a view of understanding surface tension from the molecular perspective, or what happens really at the molecular level and what gives rise to surface tension. So, let us take a vessel containing water. So, this is the level of water. Let us take 2 points, a point A here and a point B here on the surface. The molecule, the water molecule here experiences an attractive force due to all other water molecules. So, this is uniform in all directions. This is an attractive force due to all other water molecules. Now, consider this, let us call this point as A point and let us call this point as B point. There are no counterparts above. So, the force lines parallel to the surface are oppositely directed, and also there will be forces which will not be balanced by upward forces, and because of these forces downward, the liquid surface is trying to compress a little bit and the area will be minimized. Okay? And this is the same reason, this minimization of surface area is the same reason that we see the dew to be spherical in shape, or the dripping water, the last drop of water to have a spherical shape at the end of the tap, because spheres have minimum surface area, and that minimum surface area is that of a sphere. So, that is why they take spherical shape. So, the surface tension is responsible for this spherical shape of the dew that we see on the ground. Now, let us look at a relevant extension of this idea and talk about what is called as surface energy. So, there is some amount of energy needed to increase the surface area, as we have seen in this YouTube experiment that we have mentioned. So, this is that movable rod, and this film encloses, or this region encloses a thin liquid film. So, we need some amount of work to be done and apply a force in order to increase the area. So, there is this work done will be stored as some surface energy. So, this work done will be called as, or rather stored in the system as the surface energy, and the surface energy, or rather the work done to begin with, is defined as F delta x, where F is the force given and delta x is the small extension that happens because of that application of force. And this we know that can be written as S into L, because of S equal to F over L. So, F equal to S into L, and then delta x, and this is equal to S into delta A, where delta A is the increase in area that has happened because of this small extension. So, we can also write that S is equal to W over delta A, where W is the work done in the process and A is the delta A is the area, net change in area because of this work being done. So, this also can be represented in joule per meter square, and as we have seen that it is represented in Newton per meter, it is also represented as joule per meter square. We shall do another thing which is again related to this, is called as the angle of contact. you might have seen that some insects actually can walk on water, or as we have given an example earlier, that a small balloon can actually, water filled balloon, it is filled with water, it still can float on water, and that can happen even though they are denser than the liquid or the water, but it can still float, and the reason is the surface tension. So, we can calculate the angle of contact of say a sphere. So, there is a liquid film here and there is a sphere there. So, there are these surface tension acting. This is considered to be that water filled balloon that we have talked about, and this is the surface of a liquid. So, this is the surface and the liquid is below, and this water filled balloon is not getting submerged, rather it is floating, because the surface tension is acting, which is equal to F over L, and the angle of contact is given by theta. So, this has a radius r, this sphere has or the balloon has a radius r and has a weight that is acting downwards, which is due to the gravity. So, the surface tension is acting in this direction in order to support the weight. The horizontal components of the surface tension will cancel on both sides, because the horizontal components along the surface of the liquid will cancel from both the sides, and the vertical component will add up and go on to support the weight of this balloon. So, we have S cos theta surviving. The vertical component of S, if we draw theta to be like this. So, this will be the vertical component will be S cos theta. So, S cos theta is the vertical component of surface tension. And supports weight. So, water filled balloon on the surface of a liquid. So, this force is acting at all points on a circle of radius r. So, this liquid is enclosing that, and this is dipping that surface, and so we have 2 pi r s cos theta is going to support the weight of the balloon, right. So, 2 pi r coming from at each point on the, so where the sphere is dipping. So, this circle at all points this surface tension acts and will give rise to a total force upward, which balances the downward force due to the gravity and the weight of the object or the balloon in this case, and this is equal to, so cos theta will give me now equal to W over 2 pi r s, and we can calculate theta to be cos inverse W over 2 pi r s. So, this is the angle of contact of an object which floats on the surface of the liquid, surface of a liquid, and this is the angle that it makes, then this direction makes with the vertically drawn normal. So, let us see one example of this. So, write down a problem in order to explain this. So, an insect can walk on the surface of water. The base of the foot of the insect is approximately spherical with a radius (10⁻⁻⁴ meters. The insect has 6 legs. You have seen a 6-legged insect and a mass 0.002 gram. Calculate the angle theta that its legs make with the vertical. Calculate, sorry. So, this is a statement. So, calculate the angle that the angle theta that the legs make with the vertical. So, we know that 2 pi r s cosine theta equal to w. 2 pi is 3.14, we will take a sort of simpler value. So, 2 pi becomes 6.28, r is 10⁻⁻⁴ meter. Now, surface tension of water. So, now it is given that assume the temperature to be 20 degrees centigrade, which means that you have to take the surface value of the surface tension of water at 20 degrees centigrade, which is what we have said. We will write it once more. It is 0.072 Newton per meter, and that is equal to mg 2 into 10⁻⁻⁶, that is the mass, and so this is kg, and this is 9.8 into 9.8 meter per second square, but there are 6 legs. So, they will be supported. So, this 6 legs will support the total weight. So, this thing has to be divided by 6, and we need to know the angle that one of the legs the foot makes on the water. So, this if you calculate it, cos theta becomes equal to 0.33 divided by 0.90, which is equal to 0.37, and theta equal to cosine inverse 0.37 is approximately 68.2 degrees. So, this is the angle that the foot of the insect makes on the water, and it does not drown, rather it can walk on the water. And so, this is the angle of contact. There is some more interesting thing about the angle of contact, which is called as capillarity. So, we will discuss capillarity. You may have noticed that water kept in a glass of water, in a glass, the edges actually bend upward. Okay. So, this is the liquid meniscus when it is water. So, this is water. And if it is not water, say if it is mercury, then the meniscus is not like that. In fact, it gets lowered So, as the surface of a liquid touches the surface of the container that it's kept in, either where they meet, they will either rise as it does for water and it will dip for mercury. And you can explain it by an angle, let us call it as theta, and this angle is acute for this for water and the angle is obtuse for mercury, where it is measured from the vertical. So, these are the two kinds of liquid that we have, that is one of them when the surface comes in contact with the surface of the beaker or the glass or the container that it is kept in, either it rises, the liquid meniscus rises, or the liquid meniscus dips, as shown here, making either an acute angle or an obtuse angle. Now, why does this happen? That is the question. It happens because of two things. One is called as the force of cohesion and the competition between two forces. One is called as the force of cohesion, the other is called as the force of adhesion. So, force of cohesion and force of adhesion. Force of cohesion is the intermolecular force between the liquid itself. So, that is the force that one molecule exerts on another molecule, that is called as a force of cohesion. And the force of adhesion is the force that the liquid exerts on the molecules of the liquid exerts on the molecules of the glass beaker, say here, or the molecules of the container that it is kept in. So, in water, the force of adhesion is more than the force of cohesion. So, let us call it as F c as force of cohesion, and let us call this as F a as force of adhesion. So, in this case, for the case of water, we have the force of adhesion to be larger than force of cohesion. So, the water molecules are strongly attracted towards the glass molecules, and that is why they tend to move up. And just the reverse happens here, you have F c is greater than F a, which means the molecules of mercury, the force of attraction or the force of that exists between the molecules of the mercury molecules are more than the cohesive or rather the adhesive forces that is there between the molecules of mercury and the molecules of the container that it is kept in. So, these two will make, so one is that it is an acute angle that the water makes with the container and that the force of adhesion is greater than the force of cohesion, and exactly the opposite occurs for mercury, where it makes an obtuse angle with the normal, and the cohesive force between among the molecules of mercury is more than the adhesive force between the mercury and the container that it is kept in. So, we can actually calculate this theta. So, how to calculate this theta? Let us take one example as that of water, and let us just accentuate or rather emphasize it more. Say this is the meniscus, and take some height h here, and we want to calculate the height h here. This has 2r as the distance. So, this is s and this is s, this also is angle theta. We want to calculate the height that the liquid column rises from the the horizontal level. So, the surface tension act at an angle theta all around the circle, which is what we have said. Surface tension acts all around the circle of radius r. So, the magnitude of the vertical force, so magnitude of the vertically upward force due to the surface tension. So, these are the surface tension acting there due to the surface tension is F and a cos theta into L. That is the definition of surface tension, and L is equal to 2 pi r, which is equal to 2 pi r s cos theta. So, because L is equal to, since L is equal to 2 pi r, and this is going to support. So, this 2 pi r s cos theta, which is the vertically upward force, will balance the vertically downward force due to gravity, which is equal to mg, which is equal to rho v into g. And let us consider volume of a cylindrical column of water or the liquid of density rho. So, this is equal to pi r square h rho and g, where v is replaced by pi r square h, which all of you know that the volume of a cylinder is given by volume of a cylinder equal to pi r square h. So, my h, which is what I want to calculate, comes out to be 2 s cos theta by so 1 r will cancel, and this will be 2 s cos theta by rho g r, and so this is the expression for the height of rise, the capillary rise at the towards the edges of the beaker or the container containing the liquid. Here for water, theta is almost equal to 0, that is we have definitely enlarged the picture. Actually, the angle is very small, it is close to 0. So, if theta is close to 0, cos theta becomes 1, and in which case I have a simple expression h equal to 2 s by rho g r. So, knowing the surface tension of water and of course, knowing the temperature has to be specified at which we would know this S. Rho of will be known, G is of course known, and the radius of the beaker is say is given. Then you can calculate the height that is they will be recorded or noted at the edge. So, you understand that keeping all these other things same, if we take a bigger beaker or bigger glass which has more radius, then this actually goes as 1 over r. So, as r increases, h will go down. So, this height will be smaller and smaller as you have the beaker containing water becomes bigger and bigger.